PV panels. They are not mandatory, but we are moving towards a future in which, if we want to create zero energy buildings, so far, the most reliable technology that we have is this technology, the PV panels. We have thermal collectors, they are very reliable, and in most of the countries are mandatory. Not here, if it's very cold, with solar collectors, we can have problems with freezing. With the PV panels, we don't have problems. We don't have issues that can leave a house without hot water or without electricity, as long as we have a backup, as long as we are connected to the grid. So that's the first thing that we need to think about when we are working with PV panels. If you want to be on your own, if you don't want to pay any money to electric companies, or you don't want to pay any taxes about electricity or whatever, this is the perfect solution, because you can live on your own without bother or without being bothered by anyone. You design your own house, you place it, you can use the right orientation for the house so that you can generate all the energy you need. And if you don't have enough energy, it's up to you. Okay, so I can't use the washing machine today. Never mind. I can't have hot water today. No problem. I will take a shower tomorrow. I can't cook. Okay, I will fast, because we have started the Ramadan, and I can fast. Well, sometimes living with this perfect world without consuming energy takes tough decisions, but we are not this kind of society, so we are not, well, I'm not joking, because sometimes if we want to live in this sustainable world, we need to make some sacrifices. But the problem is that we are not used to doing that anymore. My parents, your grandparents, probably, so 3 generations before you, the life was very tough, and life has been tough on this world since mankind started being here. Okay, so winter is very cold, summer is very hot. You have to work to produce your food. Now it's easier. Now everything is easier. But if we listen to some of the messages that we are receiving, it seems that to achieve this sustainable goal, living in a world in which we don't emit CO2 to the atmosphere or these greenhouse effect gases, it comes at a price. And what is the price? There are 2 prices. One, we lower the standard of living that we are used to, or we pay more. Nowadays, it seems that we have to pay more, okay? Because we are not renewable yet, so we don't have enough renewable sources of energy to generate all the energy that we need. So basically, I don't know who they is, but the prices of the energy have risen a lot. So we have to pay more. Just if we want to cook every day, okay, pay more. The gas bill has increased. If we want to have electric energy, pay more, that's fine. So it comes at a price. The other way we have nowadays to do that is to renounce to our standard of living. We are used to turn. Okay, so we can click here and something happens. The lights turn on, or we have the projector, or we have a computer. So we have electricity available. If we are working only with PV panels, we don't have this, or probably we won't be able to have electricity just whenever we feel like. So we have to think, okay, when do I want the electricity? When do I need the electricity? At this time? Do I have electricity at this time? Do I have sun? No, I don't. Then I need batteries. Okay, so nowadays being sustainable or being zero energy comes at a price. And we have to rethink our way of living. Does it make sense? Well, I don't know, but technology is not perfect yet. We have much more options that we had 50 years ago, but and we know more, and we have better materials, but we are not at that time in which everything can be renewable, and we can keep living the same life that we have lived over the last 40 or 50 years. Okay, so we have to be aware of that. Anyway, the first thing we have to decide is what kind of schematic we want for the PV. I think we have talked about this before in other courses, but you can, the first option would be the PV array plus energy from the grid. With this, you are not 100% renewable, because when you don't have sun, you have to take energy from the grid. So someone has to generate that electricity. So if there is no sun, or during the night, if you want to turn on something that runs on electricity, then you need to take this electricity from the grid, and you have to pay for it. And you have to connect your house to that electricity. So that's the first option. This is what I would do right now, at this moment. Why? Because PV arrays, they are reliable, but we have sun or we don't have sun. If we don't have sun, we are not generating electricity. If we don't have electricity, we either don't use electricity when we don't have sun, or we take the energy from the grid. Okay, so nowadays, I think this is the best option. There's another option, which is the off-grid system. And then we need batteries. Batteries now, right now, they are very expensive, and they take up a lot of space. So if we want to go off-grid, if we want to live on our own without paying any electricity or any electricity bill to the electric companies, or without paying any taxes on electricity or on energy, we can do that. But what is the price that we have to pay? A lot of money for batteries and a lot of space. Okay, so again, being sustainable comes at a price. In this case, we have to pay a lot of money up front, and we need to, well, one of the rooms, it's going to be occupied with batteries. And we always need a backup generator. Okay, so yes, we are sustainable, but when there's an outage or something like that, in winter, when it's very cold and we have snow, and we don't see the sun for 3-4 days, or something is wrong with the batteries, or, well, when we didn't have an issue, we have a backup generator, and usually it burns some oil. Okay, so we just and that starts burning oil, gas, or whatever, and then we have a backup generator. So this concept of backup, it's something important. Even countries have a backup energy. A percentage of the energy that we are consuming, it comes from renewable sources. But what if we don't have these renewable sources? What if we don't have sun? What if we don't have wind? Then we need the backup. And backup now, in this moment of history of mankind, is always about burning something. We can burn coal, the worst thing we can do. We can burn gas, okay? We can burn oil, but it's always about burning. So this is our backup generator. We wish we didn't have to burn oil, but this is what happens nowadays. So even with an off-grid system, if you want to be off-grid, you need this backup generator, and don't forget it, because it can happen that for a week or for a couple of days or for, I don't know, a period of time, you don't have energy because there is no sun, or because the snow has is here and it didn't melt and you can generate electricity, or because your battery system is not working well, so you need a backup generator. That's why I would use this option. If I don't want to run any risks, I have the PVarray, I have electricity from the grid. If the PVarray is not working, I pay energy from the grid. If we are within an urban area, we can do this easily. If we are in the middle of the forest, 50 miles away from the main road, and we don't have access, probably that would be the best option. But if we are in an urban area with easy access to electricity, this is what I would do. But this is the first option that we have to make. Okay, so PVarray with energy from the grid or off-grid system. The off-grid is the same as the standalone system. And well, the standalone system, basically we need batteries, and then we need all this, but all this, the DC, the charge controller, the inverter, those are things that we need for this option too. Then we need to know the consumption of our appliances. Again, do we want to be sustainable? Don't use clothes dryer or a hair dryer or a burner or a cook or an electric cook. I know there are a lot of alternatives. But if we want to have the same appliances that we have that we are used to, hair dryer. Now I want to boil a couple of eggs for the breakfast. Okay, my electric cook. And okay, if we want all these facilities, if we want all these appliances, then we need to know how much energy they consume. And well, this gives us an idea of what we need. This is the what. What is the instant consumption? And again, we have power and we have energy. We have something that consumes a lot of power with the central air conditioner or heat pump. Basically, this is the heating or cooling system. So you see that this is the highest number in terms of watts. Is it the highest number in terms of energy? We have to multiply this times hours. Okay, so how many hours are we using the heating system in winter? A lot of hours. So the heating system is the appliance that has the highest power and also the highest energy, because it's running a lot of time, a lot of hours. So to get the energy, we have to multiply power times time. What about a hair dryer? Yes, a hair dryer consumes a lot of power, 1200. But how many hours a day are we using the hair dryer? Well, it depends. It depends on your hair. But well, it's a few minutes. Okay, so it's not a big deal, because even if it's consuming a lot of power, if I use this only 10 or 15 minutes a day, so you won't notice that. What about the refrigerator? A refrigerator, how many hours is it working? 24 hours. It doesn't mean that 24 hours the refrigerator is consuming energy. It has cycles. Okay, so maybe it's freezing for a couple of hours, and then we have a couple of hours that it keeps the temperature. But refrigerator, usually it's something that consumes a lot of energy. Okay, then what about a desktop computer? It doesn't consume a lot of power, but it depends on how many hours it's on. So usually we leave home and the computer is on for, I don't know, 12 hours without using it. Is it a big deal? Well, here it's 4 cents per hour. If we use this 10 hours, if we are not using the monitor or the computer for 10 hours a day, so it's 40 cents a day times 365. Let's do 40 cents a day times 365 days is 14,600 cents. So it's $146 a year. So if you leave your home and you turn off your computer, this is one computer. If we have 3 or 4 computers on all day, so at the end we are paying hundreds of dollars more than we should. Okay, and this is energy that we are wasting. We can't do that if we are off grid. Because what's the point of using the energy that we have in our batteries if we are wasting this energy? Okay, so that's what I mean, that if you want to live on your own, if you want to live off grid, you have to change your behavior, and probably leaving the computer on for 10 hours a day, even if you are not home, it doesn't make any sense, because you will be consuming this energy. And when you're off grid, when you are connected to the grid, it's just about paying $100 or $150 more per year. It's $10 per month. Okay, can you afford it? Probably you can afford it. But if you are working with your own energy, if you are storing your energy in batteries, this doesn't make any sense. Okay, so we need to understand this. We need to understand that we have power and then we have energy. So this is the power that appliances are consuming, but to understand the energy that we need to multiply this by hours. And that's we have to understand that. And a light bulb, if it's incandescent, it's 60 watts. If it's LED, it's 10 watts. Okay, so basically what we are doing, if we are using LED lights, we are saving a lot of energy. If we have the LED lights on a lot of time. Okay, so nobody is using incandescent light bulbs anymore. Everybody uses LED lights, and we don't have to do anything to persuade people to do that. It's natural. Why? Because they notice. LED lights are more efficient, they last more, they consume less energy. So when you have this, you don't have to give incentives, subsidies to use LED lights. Everybody would do it. Okay. So we need to know that. And when we have these specifications of our appliances, this refrigerator is 1,000 watts. Well, it depends. We have different categories for refrigerators. We have the Energy Star, whatever. So we have, it's our commitment to select the best appliances that we can find on the market. Because with this, we will be saving energy for us, for our clients, or whatever. But we have to understand this. The heating and cooling system, it has the highest power, and probably we are using this a lot of hours. So the 50% of the energy that we are using in a house or in a building, it's about well, in single family houses. In other buildings, in this building, we have thousands of light bulbs. So probably artificial lighting is important. But in single family houses or in small buildings, 50% of the energy is about the heating and the cooling. Okay, so we need to know this. This is another chart. Here we have low consumption appliances, but a lot of hours. Okay, so we have LED lights. A LED light, in this case, it's 8 watts. In this table, it was 10. Okay. But we use a LED light a lot of hours per year. Probably the kettle or the microwave, it's something that we use only 30 minutes per day. Or the cooker, it's only that we use 7 minutes per day. Well, depends on what you are cooking. Okay. The refrigerator, you use it 5 hours. It means that you have cycles. 5 hours. This is very optimistic. Okay, so this is something that consumes quite a lot of energy and you use it a lot of time. So probably the refrigerator is something that you have to, you have to consider when you're purchasing this refrigerator. And then we have television, the computers. So here we have low consumption appliances, we have high consumption appliances, and this is the hours that we are using the appliances per day. This is for single family houses. We are not, we don't have all these appliances in public buildings. We don't have, we can have microwaves, but it doesn't matter a lot. So the first thing we have to do is to understand the monthly demand in the electric monthly demand. It's very easy. We know the power of an appliance, of one of the appliances, then we multiply this by the number of hours that we use that appliance, and then we have the monthly demand. But if we want to calculate a PV system, this is the first thing that we have to do. We have to calculate the monthly demand of all the appliances. So it's the power of the heating system times the hours per month that we are using it. So for example, we are used to the heating system. If we open the Excel file, if we open the Excel file, what we have here, this number is the heating load. Okay, so we have the area of the roof, we have the U value of the roof, and we have the difference, the temperature difference between indoor and outdoor temperature. So the value that we have here is the power. Okay, it's the heating load is the power. And then we need to add up all this. We have the power that we need, or the thermal load that we need through the walls, the thermal load that we have through the floors, through the roof, through the windows. So at the end, we have the thermal heating load, and this is what we call the peak heating load. If we want to understand the energy that we are using, we have to multiply this number times the number of hours that we are using the heating system at home. And this is what we are doing here. Okay, so I haven't talked about this part of the Excel file yet, but in this case, we have the different months. These are the days per month, 31, 28, 31, 30, so on. And this is the operating hours per month. So that depends on this element here. You see that here we have the operating days per week and the operating hours per day. So this is the schedule of the building. If we are working with a single family house, probably we will be working with 7 days, 24 hours. But are we 24 hours at home? It depends. If you are only, I don't know, 15 hours at home, then you will be operating this system only for 7 days a week for 15 hours per day. And here, this table, when you change this, you see that the values of the chart change because this table takes into account the schedule. Okay, so it takes into account the U value and the area of the walls, and this is the operating hours. So it's the operating hours per month. If we are operating this 6 days per week, and if we are operating this 15 days per hour, and we have a month with 31 days, so these are the operating hours that we have here. Okay, so that's the explanation of this table. We have to change this depending on the schedule, If it's a public building and it works only from Monday to Friday and only from 8 a.m. to 8 p.m., so that would be a 5-day building with 12 hours. Okay, so you see that this row is changing, and it's changing depending on the operating hours. Then what's this? This is the outdoor temperature, but this is the outdoor temperature. Okay, it's not the same as this outdoor temperature. We are using this outdoor on the worst case scenario. So we are using this if we are we are calculating heating loads. We are using this outdoor temperature as the coldest temperature that we can have. But in this case, in this row, what am I considering? I'm considering the outdoor temperature, but it's the mean outdoor temperature in this month. Where can we find this? There are a lot of websites. Okay, so in January, the average temperature ranging between a maximum of 27 and a minimum of 15 Fahrenheit. Okay, so this is the average temperature in Kim. So the maximum average temperature is 27, the minimum average temperature is 15.1. So one day we can have a -2 or -5, but the average minimum temperature in Kim would be, in January, would be 15. Okay, so this is what we should use here. If the minimum average temperature is 15 in January, this is what we are doing. What about February? In February, the lowest or the average low is 16.5. So here I should type 16.5. Okay, so with this table, we are using the operating hours per month, and we have to select not the lowest temperature, we have to select the average temperature in January, in February. Okay, so that's why this will change. And here we have the total energy in BTUs that we need on a monthly basis. Okay, so here we have the energy that we lose from the walls, the floors, the roof, the windows, ventilation, infiltration. And here we have the window solar heat gains. So at the end, we have losses and we have gains. In summer, everything is gained. Okay, we gain heat through the wall, we gain heat through the roof, and we gain heat through the windows. In winter, through the windows, we have gains through the rest of through the walls, through the roof, and we have losses because the temperature is very low. Okay, so this is how it works. And when we are calculating the PV array, we need to take into account the monthly values. Okay, so we cannot calculate this with the peak load that we have calculated with the lowest temperature that we can have in Kim. We have to calculate this with the average temperature in different months. When we are calculating PV arrays, we need graphics like this. We need graphics on a monthly basis. We need to know the amount of energy that we are using. it can be, and if we are generating electricity, we need kilowatt hours. Okay, so BTUs is not the units that we need for calculating PV arrays. It's always kilowatt hours. So at some point, we have to turn this into kilowatt hours. Okay, but just knowing the power is not enough. We need to know the energy. So we have to multiply power times the number of hours that we're using this device or this appliance. Okay, so before analyzing anything, we can calculate the potential of the PV production in our roof. Okay, so this would be the maximum PV production that we can have. Okay, that's a figure, that's fine. But we can, if we want to match the PV production and the energy consumption, we need to break down the energy consumption in different months. Okay. And we can use F-chart, we can use PV watts, or we can use Revit. So first, make a decision about this. Most of your projects would be this option, a PV array plus energy from the grid. We're not going to teach how to dimension batteries. It's too complicated. And okay, so we're going to decide on this option, but you have to realize that we are using this option. We have a PV array. Probably we won't cover 100% of our energy with the PV array. So we need energy from the grid because we won't have batteries. Second, we need this analysis. We need to understand if you're working with a residential building, you can do this with one of the apartments and multiply this by 50 apartments or 60 apartments. So that will be the, so we need an analysis of the appliances that we have in that apartment. If we are in a public building, then we have to do a research. If we are working in this building, how many lamps do we have in every room? What's the power of this ramp? What's the power of the projector? What's the power of the computers? Well, we can take this. A desktop is 400 watts. How many computers we have here? 16. These computers are always on, by the way, you know. Okay, so we have the saving energy. So when the computer is has not been used for a few minutes, it enters the saving mode, but it's consuming some energy, probably not 400 watts, but maybe 50 or 60 watts if it's on this saving. Well, we don't know. But these kind of things are in the specification of the computer. What is the consumption of the computer when the monitor is on and the computer is on? And what is the consumption when it's on this saving state? Okay. And it takes a lot. I mean, we need a database with all these things. So this is probably the most difficult thing that we have to do when we are analyzing buildings, especially public buildings. And we have to do this when the building is not done yet, because now it's easy. How many computers? 1, 2, 3, 7, 17 computers. Okay. What is the brand of the computer? Dell. Perfect. So we can go to the specifications and knowing that. And what is this microphone? Whatever. And what is this projector? Whatever. So when the building is done, we can easily understand the sources of energy. If we are designing the building, we don't have any idea. We have to. But we can have a good PV analysis without having this graphic, because the PV production will change, and it will be different in January than in July or August. So we have to try to match the energy production to the energy consumption. So that's the biggest challenge that we can have when we are analyzing or when we are designing a PV array. So let's use this, okay? Imagine that we are working with this, okay, we are just designing a PVarray for heating loads, for heating and cooling loads. And this is the result. Okay, so here we have BTUs, 5 million. So the first thing we have to do is to turn these BTUs into kilowatt hours. If we want to do that, I have to unprotect the sheet. Okay, now it's not protected, and I would need another row here in kilowatt hours. And it's the other way around. So what's the conversion between BTU and kilowatt hours? We have to find out BTU to kilowatt hour conversion. So 1 BTU is this 0.000. Okay, let's see. So that will be this times this number. Okay, and now I want to format with just 2 decimals, and I do this. There you go. Okay, so according to this, I'm consuming 1,700 kilowatt hours in January, 1,500 in February, 1,600 and so on and so forth. When we have negative, that means that this is heating and this is cooling. But negative doesn't mean that I'm not consuming. It's just a difference between heating and cooling. Okay, so this is the first thing that we should do. Turn our BTU energy loads into kilowatt hours. Okay, now let's use PV watts today. PV watts calculator. We are in Keene, New Hampshire. And okay, so now we have to design the system size. So the first thing we have to analyze is the tilt, the angle of the PV panels, and then we have to design the azimuth is the orientation of the PV panels. 180 would be the best orientation because we are, this is south. If you want to orient your PV panels in other orientations, don't do it with the north orientation. It doesn't make any sense. But if it's south, southeast, southwest, we can change the angle here. So imagine that we are using the default options. We have 180. Here we have 20 degrees. And here we have the module type. I think I've explained that before, but anyway, we have the standard, the premium, and the thin film. What is the thin film? No. Hmm? What is it?
Oh, wait, never mind.
No, is that I don't get the thin. Well, there are different technologies. What are the technologies of a PV panel? There are 2 main technologies. Thin film is one of them. What's the opposite to thin film? the crystalline technology. Okay, so this is what we are used to. 90% of the PV panels are crystalline technology. It can be polycrystalline or crystalline. So there is no difference, but we have them monocrystalline or polycrystalline. Oh. Okay, so we have these two technologies. Or vice versa.
Hi, I'm Finn Peacock, founder of Solar Quotes. I get approached all the time by confused homeowners who've been quoted solar. And they've had the salesman enthusiastically sell them on the merits of their mono or poly panels. The funny thing is, the salesman is always talking up the type of panel that they happen to be selling while rubbishing the other. It's always amusing to hear from someone who has two quotes, one using mono panels and the other using poly, with both salespeople rubbishing the other's type. I'm here to keep it simple. The two panels have similar wattage. The difference in performance between mono and poly is absolutely tiny. So don't stress over it at all. All you need to do is pick a good brand and you'll be set. Now, to make things a little more confusing, there's recently a third type of panel technology hit the market. It's known as cast mono, which is basically a hybrid between mono and poly technologies. But my advice here is the same. The differences in performance is almost nothing. So it doesn't matter if you get mono, if you get poly, if you get cast mono. What's important is that you buy a good brand that will last 25 plus years on your roof.
Is it clear? Mono, poly, cast, mono, whatever, is always the same. But what if we compare crystalline versus thin film technology? Or amorphous panels. Well, here the technology matters. So let's try to. Okay, we can have this thin film solar cells. It's the amorphous silicon thin film. Okay, so those are synonymous, the amorphous silicon or thin film panel. But the thin film is amazing because, as you can see, it can it's not rigid, it can be flexible, it can be transparent. So it's something that architects like, because if we have a PV panel with these dark cells, well, we don't like it because it's like, we usually don't like it, and we don't think of this as the finish of our wall or the finish of our roof. Usually it's something that we put above the roof, but it's not part of the envelope of the building. The thin film, it's amazing because it can be transparent. So this could be a PV panel and it could be producing energy. The problem is that the efficiency of this amorphous or thin film PV panel, it's half of the other one. So the efficiency of a PV panel, it's 10 to 12%. The efficiency of a thin film, it's 5 to 6%. And the price, it's not cheaper. The thin film is not cheaper than the other one. Okay, so usually if you want to maximize the production, you have to go to the crystalline, either mono or polycrystalline. But if you want to integrate PV panels into architectural design, Usually, architects decide on the thin film. I think I have recommended this before. Onyx Solar. These are my friends from Onyx, and they work with. They try to create something new, or they try to do something creative with this kind of PV technology. So here we have different panels, hexagonal panels, and we can combine both technologies. So those are the crystalline technologies, and those are the thin film. Thin film are more flexible. You can use different colors. You can use different transparency. With the crystalline PV panels, it's always the same. You have to use the same cell always, and that's it. They have outstanding projects. We have a photovoltaic curtain wall. So that would be the thin film. Okay, so if you have this, you don't notice that you have a PV panel here, but it's producing energy. So basically, the thin film. Well, you can have different options for the thin film panel, but okay, and this is something that you can do too. I don't know if you notice, but in this case, we have the cells. So this would be the crystalline or the polycrystalline panel, but the cells are not close to each other. So you have this feeling of transparency. You have a transparent glass with cells here. Okay, there are options. The most efficient way is using a crystalline cell. And crystalline cells are always something like that. They are black or dark gray because they are made of silicon. Okay, and if there's another cell here, they have to be connected. So those are two metallic connectors. Okay, so when we have this crystalline and the mono or poly crystalline cells, usually it's something like that. We have the black or dark gray cells, and then we have wires connecting them. At the end, we have a positive one, we have a negative one, a positive one, a negative one. So at the end, we connect all the positives, we connect all the negatives, and then we have tension between the positive and the negative. Here we have tension. So this is the electricity that we are generating. What we are generating here is direct current. 90% of the devices that we have at home, they run on alternate current. Okay, so here we need an inverter. We can, if we run devices on direct current, we can have a device here. Okay, so this is something that when we are designing PV arrays, this is something that we have to take into account. If we generate direct current and we have devices that run on direct current, there are very few in the market, but there are. Okay, so we save the inverter because everything that we have something in the middle, everything that we have to convert something into something different, and we lose energy here. Okay, so there will be losses. So if we find devices that run in direct current, we are saving energy as well. So this is something that we have to keep in mind. Anyway, the efficiency of crystalline panels, the efficiency is around 10 to 15%. 15% would be something. So that guy told us, select a good brand. Okay, a good brand would be close to 15%. A bad brand would be 10 or lower. But if we are talking about thin film or amorphous technology, the efficiency would be around 5 to 6. Okay, so that means that we need twice as many panels with this technology than with this technology. Yes, it's great because it's this technology is transparent, and probably if we can look at some of the projects that those guys are doing, they are very good at this. Okay, so that would be an envelope or a curtain wall made of these crystalline panels. You see that we see the cells, but they are not completely attached to each other, and we have this feeling of transparency. So it looks good. We have these effects of lights and shadows. It looks good. What's the, yes, and here we have a picture of the facade itself. Okay, so here we have the picture of the facade. This is the Balenciaga in Miami. Okay, good. Do we have more projects? I want to see Skylights. Okay, those Skylights seem thin film panels because we don't see the cell. Okay, so we have a huge skylight with the right orientation. It's almost transparent. We can see through it. And here you see that we don't have the cells. So we have it's completely transparent. So probably that will be the thin film technology. And what else? Let's see. A photovoltaic skylight in McDonald's. Okay, so this is the typical cell, the typical crystalline, poly or monocrystalline cell. Okay, so you can do something appealing with this kind of technology. This is a canopy, so this is an open area with a roof. You have shade because here you don't want to be under the sun, especially in Miami. So you need this this shade. So it looks nice. Okay, so there are design opportunities, and little by little, architects are integrating this technology into good design. And at night it looks good too, but at night it's not producing any energy. But yeah, during the day, so nice. But basically, that's the difference between the crystalline and the thin film technology. Thin film, you can have this sense of transparency, which is important. With the crystalline technology, it's not transparent. And the wider or the, yeah, we can place another cell here. Okay, so this will be the dark gray. And this is dark gray, and this is transparent. And again, the more transparent gaps between two cells, the less the production. So this is much more effective than this. So it's a question of what you want. It's a question of what the client needs, and it's a question of the money that you have to pay compared to the energy that you are producing. But this is the efficiency. The maximum efficiency is 15%. Then if you want to do something like that, probably the efficiency is less. Even though the cell is very good, it's a very good quality. If you leave those gaps between different cells, the efficiency drops. So, and here you have technical specifications about the panels they are working with. Let's see okay, so this is the amorphous silicon PV glass. So that would be the thin film. Those are the standard sizes. The thickness, the transparency, and this is the peak power. So this is the peak power that they can produce. Okay, so here we have 57.6 watts per square meter. Here we have 40, 34, 28. Okay, and this is high transparency. The more transparent, the less the production. It makes sense. Okay, so when we have something dark, the production is quite high. If it's very transparent, and then the production is very low. So this is the thin film, and they place the thin film at the beginning because, well, they work for architects, and usually architects prefer the thin film over the other one. But they do have the crystalline silicon PV glass. And with this, they don't have information about the PV production here. No, they don't. Well, they would have in other place of the website. They had a wonderful calculator, but I think they don't have it anymore. They had a calculator to compare both technologies, but products, consulting, yeah, I think they don't have it available on the website anymore. Anyway, they are working here. They are working in the United States, and this is one of the Onyx. It's one of the companies that are trying to integrate PV panels into good architecture. So all the projects that you see from them, they have something special. They are good architecture, and they are good examples of integrating PV panels and architecture. So take a look at it, and let's see what they are doing, either with crystalline or thin film PV panels. But they have a lot of examples of good integration. Anyway, in PV watts, because this is what we were doing, we have to calculate first the module type. We have the standard, the premium, or the thin film. Premium would be an efficiency around, it would be a crystalline with a high efficiency, close to 15%. Thin film would be, well, there will be an efficiency close to 5-6%. Let's use premium, okay? Then, is it a fixed open rack or is it a roof mount? Open rack. Is something like this, okay? So we mount the structure and the panels on it, and the roof mounted is this, okay? So we make the most of the slope of the roof. What is the best solution? I think the open rack is more efficient, but it's more difficult to integrate. At least if we have a roof and we follow the same slope, we're not adding anything else. The open rack, yeah, so we need to mount the structure, and then you see we can get the optimum tilt or the optimum angle for the panels. So let's use open rack, and then the system losses, that depends on the shadows, that depends on the efficiency of the panel, it depends on the system. So let's leave it like this, and let's do it. And then this is the DC system size. This is what we have to find, okay? So now we have to find the DC system size. So if we have a premium panel with a fixed open rack, the angle of the panel, it's let's change it to 40, and the azimuth is 180, so it's south oriented, and we have these losses. These are standard losses. then we have to calculate the production. Okay, so this is the useful alternate current energy that we have generated, 386 kilowatt hours in January. What is our demand? Our demand was 1700 kilowatt hours. Okay, so we should type here the PV production. Okay, so this is the PV production, and now we will have to type here this value. In January, it's 386. In February, it's 424, 507, 480, 515, 5458, 520, 8, 4, 8, 7, 8, 9, 4, 8, 6, 3, 4, 7. Okay, so this is the PV production. If we want to calculate the F factor, this is what we will do with the F chart. What's the F factor? It's the percentage of the total energy that we need with the PV panel. What's the formula of that? That will be this divided by the total energy and multiplied by 100 times. Okay, so that's the meaning of the F factor. Is 22%. So I want to format. Okay, is 22% or point? Well, if we don't include the 100, is 0.23. And well, if it's negative, it's just heating or cooling, but it doesn't affect so what happens here? So there's a month in this case in which we are producing more than one. So this is more than 100% of the energy that we are producing. So here we produce only the 23%, the 28%, the 30%, 50%. Well, those numbers don't make any sense because I haven't calculated anything feasible. It's just to show you how we have to work. Okay, so we have the heating loads, then we have to work with this. Here we are working with the average temperature of each month. We calculate the heating and cooling loads, and then we calculate the demand with this. If the demand is more than, if the F factor is more than 1, that means that we are generating more energy than we need. If it's less than 1, that means that we're generating only the 23% or the 28% of the energy that we need in this. Okay, so this is just an example. I don't know the heating loads or the values that I have used here. Usually when we are calculating the F value with the roof that we have available in our building, usually it's never more than 20–30%. I told you that this huge PV array that we have here is around 30% of the energy needs that we need in the building. Okay, because here everything is electric, heating and cooling is electric, lighting, computers, everything. So this is like this huge PV array that we have there is only 20–30%, depends on the day, of the energy that we need here. The only thing I have to explain, it's where this DC system size comes from. Okay, so here we should look at the specifications of where is the Onyx? Technical specifications. Okay, this is the value that we need for the PV array. Okay, so this is a 57 peak watt or watt peak. If the peak production is 57.6 watts, 0.6 watts per square meter, how many square meters we have in, or how many square feet each 1 square meter is around 10. So this is 5.76 watts per square foot. Okay, because 1 square meter is around, it's 9 point something, but it's around 10 square feet. Okay, so we produce 5.6 watts per square feet. If the DC system size is 4 kilowatts, if DC system is 4 kilowatts, that means that we have 4,000 watts. So what's the area of the PV array? It's 4,000 divided by 5.76 4,000 divided by 5.76. It's 694 square feet. Okay. So how can we calculate? Well, we can do this, or we can do it the other way around. If we have the DC system and we have the specifications of the PV panel, then we can calculate the area. Or if we have the area and we have the specifications, then we can calculate the DC system. Okay, so we can do it the other way around. If this is the peak production of my element, if I have an area of 1,000 feet square, what is the DC size of the system? It will be 1,000 feet square times 5.76 watts per square feet. So my DC system size will be 5,760 watts or 5.67 kilowatts. Okay, so if you know the area of your roof, that would be the area of the roof. This is the peak production of the panel that you are selecting. Then you can calculate the DC size of the system. And this is the number that you have to put here. Okay. So if you know the DC size of the system, and if you know the specifications of the panel, you can calculate the area of your PV array, or if you have the area of the PV array and you have the specifications of the panel, then you can calculate the DC size of the system. You have to place here the DC size of the system. It's 5.76. And then you run the simulation again. And here you have different numbers. And then you can compare the production to the demand. Okay, so by doing this, we know if the PV production matches the demand, but on a monthly basis. Okay, so here the biggest demand is in January, or even in December. In December, it's even bigger than in January. And the highest production is in June, July. Yeah, it makes sense. So the highest production is when we have sun, but the biggest demand, if we are using this for the heating system, it's in January. So how we can match these two things? Okay, we will see. We are